Okay, so for this second problem, now we need to evaluate a couple of different parameters for, again, an induction motor for which the output power is given as 25 horsepowers, the input power supply is a three-phase 220 volt 64 ampere power supply. It's operating at 60 hertz, and the operating angular speed is 830 rpm. The motor is drawing in 20,800 watts when operating at full load. So we need to calculate what is the slip percent regulation if the no load speed is 895, power factor, torque, and efficiency. So let's start off with part A. So again, we'll be using the same equations as the last one, but now we need to calculate slip rather than the speed of the rotor. So we again use the 120 times frequency divided by poles formula. And since the numbers are the same when it comes to the frequency and number of poles from the last problem, it's the same. And now to calculate slip, so S is given by the speed of the magnetic field minus the speed of the rotor divided by the speed of the magnetic field. So you have 900 minus 830 divided by 900, and this will give you around 0.078 or 7.8%. Moving on to part B now. So in part B, they are asking us what is the percentage regulation when the no load speed is 895. So this is something that I did get some questions on, and the formula for this is not there in the lecture notes, but it is given in the reading material chapter 5 for the class notes part 1 that's given for the unit. And in chapter 5 you can find out that there is a percentage regulation formula for voltage as well as speed. So here we are using the formula for speed, and let's find out what that would be. So the formula for this is given such that it is the no load speed minus the load speed divided by the load speed. So for our case here, based on all the numbers that have been given to us, it would be 895 minus 830 divided by 830. And when you plug in these numbers for this part as well, you end up with an answer that is around 7.8%. Moving on to part C, power factor. So power factor is given by an expression that looks like this. It is the ratio of true power, and true power here means the energy that the motor is drawing. So this is the input energy going into the motor. So that is the 20,800 watts divided by the apparent power. And the apparent power is evaluated evaluated differently for a three-phase and a single-phase power supply. So since here it's a three-phase supply, I'll just write down what formula you would want to use. So for a three-phase supply, it is given by √3 times the voltage times the current. If it was a single phase supply, it would have been just the voltage times current. So for this case, we need the three-phase supply expression, and plugging in those numbers over here, we would have 20,800 watts, and then in the denominator we would have √3 220 volts times 64 amps. And finally this would give us the power factor as 0.853. Now the power factor is a number that lies between -1 and 1, and depending on if it's between -1 and 0, or if it's between 0 and 1, there are two things that can happen. So when it's between 0 and 1, we say that the current lags voltage, and that is the case over here. But let's say if we had the power factor between -1 and 0, the current leads the voltage in that case. Alright, so now moving on to part D, we need to calculate torque. So here they have already given us what is the output power, and they've also given us the operating angular velocity at that for that load. So we know what the torque would be just by using the expression that power equals torque times omega. So we can just use that expression over here and find out the torque. So this output power is 25 horsepower. Now we want to convert this to watts to get an answer in the SI unit system. So you can multiply it with 746, and we have 830 RPM, which we can convert to radians per second using that expression over there. So this would give us finally 214.5 Newton meters. Let's say we wanted to find this out in the imperial unit system. We could calculate it as 25 horsepower times this conversion factor over here and 830 RPM, which would give us 158.2 pound-feet. Alright, and finally we have part E. Let's have a look at that. So the efficiency. So efficiency, as you guys know, is defined by the output power divided by the input power. So this in this case we have the output as 25 horsepower. Let's convert that to watts as well, and the input power, as you guys saw, is 20,800 watts. And plugging in these numbers, you will see that the value here is 0.897, or we can say that it's 89.7% efficient.